So now that Bohr's model of the atom has been disproven, we need to try and figure out what comes next. And the next model is really dependent upon the work of a multitude of different scientists, including Werner Heisenberg, Albert Einstein, Erwin Schrodinger, a ton of different people. But what it really took was a different understanding about the nature of matter, specifically about the nature of electrons. And there was an extremely important experiment called the double-slit or two-slit experiment, which actually helped people understand what electrons really are.
So, what they taught us in school isn't really the way it is, and that our senses are playing tricks on us. We just gotta wonder, what is this reality that we find ourselves in? Quantum physics says it's all just waves of information. Do I believe that? I hope so. Yikes! And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now, there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter, through. So we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. Physicists were completely baffled by this. So, they decided to peek and see which slit actually goes goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of any. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. It was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
So at this point, scientists were starting to understand that electrons can behave both as particles and as waves. Now, the scientists that led up to this were only under the assumption that an electron acted like a particle. So the physics and the math that they used in making their models of the atom only operated with that assumption. If we start to treat an electron like a wave, the picture really changes. So instead of thinking about the electron orbiting the nucleus like a planet around the sun, let's instead start to think about it moving like a wave around the center nucleus. And the guy who really gets a lot of credit for this is Schrodinger, and he really develops what we now know as the quantum model of the atom. And he realizes that an electron moving like a wave is going to be limited in the amount of space that it can actually take up as far as kind of connecting the wave all the way around the atom. And if you connect that wave all the way around the nucleus and then you spin it in 3D space, you get these really strange pictures that start to emerge. So just to kind of help you visualize that, this is kind of what it looks like. So if you can think about one wave being connected 3D around an atom, it's going to kind of look more circular. 2 waves, you're going to get some weird bumps. 3 waves, and it gets even weirder. So this is just the 2D image. The 3D image looks even stranger. And Schrodinger really actually develops the math that shows these things in 3-dimensional space. And that is not math that we want to be doing right now. But these are the pictures that emerge after you go and you graph the math that he was doing. And it's a series of these weird, almost balloon-like shapes that he then kind of groups together in these letters. So one big kind of just balloon looks like he calls it the S shape. Then there are 3 very similar shapes shown here in purple that are basically like 2 balloons connected. And in the X, Y, Z coordinate system, they would line up with the X-axis, the Y-axis, and the Z-axis. And then the D-shape system, there are 5 separate shapes altogether, and they look even weirder. 4 out of the 5 of them look like there are 4 balloons held together at the center, and then just oriented differently in the XYZ coordinate system. And then the last one looks like a P cloud with a big donut around the center. Really, really strange. Now, what all of these pictures represent is basically the living space for where 2 electrons can exist. And I would like to show you what that actually looks like all together. So this is a model of the atom. And we're going to slowly kind of work our way from the nucleus all the way out. And then every what they call orbital or probability cloud, where a picture of where the electrons probably are, is going to build on top of this. And I just want you to imagine, as you're watching this, actually having to draw this on a piece of paper. So we're going to start off with the smallest orbital, just a circular orbital called the s orbital. In the next shell, we start off with an s orbital, but then we're going to add in some p orbitals. Remember that there are 3 p orbitals. Each one can house 2 electrons. So here's p orbital 1, p orbital number 2, p orbital number 3. Now we move up to the next shell, and again we start with S. This is like a big bubble that just surrounds everything. P cloud number 1, so 2 electrons would live there. Next P cloud, another 2 electrons could live in this space. Third P cloud, 2 electrons would live in this space. Next energy level, the 4th energy level, an S cloud, 2 electrons could live in this space. A weird D cloud, 2 electrons would live there. Another D. Another D. Yet another D. And you guessed it, another D cloud. Now as you're taking a look at all this, could you imagine drawing this on a piece of paper and having it make any sense? Bohr's model of the atom with the concentric rings is a lot easier, but this is a lot more accurate as to what the actual picture of the atom looks like. So what we're heading toward is there must be an easier way of drawing this atom to try and make sure that we have an accurate and full and complete picture of what the real atom is really going to look like. And that method we know as electron configuration.